So today we will discuss what is inductance and what is inductor. So now you consider a coil maybe contains n number of wounds and length of the coil may be L. So if you establish current in that coil, when you establish current in the coil, that produces magnetic field inside that coil. So when you see the magnetic field inside the coil, the same field will go through the coil. The same field will go through the coil, and now you can calculate what is the flux that is going through the coil. So that flux is, I am writing here, that flux equals to, that flux will be proportional to current. So let us take this case here. So now I am taking an inductor. Let us take inductor is like your solenoid. It's a coil. Say total number of turns, or let us say n. So when you send magnetic field through this, or when you establish current in this coil, then you will see the magnetic field. Assume that B is magnetic field, and area of each coil is, let us say, A. Here area of each turn is A, let us say, and you are sending current I. Because of that you are getting magnetic field B, let us say. Then what is the flux that is going through each loop? So the flux going through each loop equals to, you get B dot A or BA, and you are not changing the radius of the coil, so A remains constant. And if you change B, if you increase current, we know the magnetic field inside this solenoid is equals to B equals to mu 0 times Ni, and N is number of turns per unit length, maybe L is length of the inductor. So as you increase I, then B changes. When B changes, then you see d phi. So now if you establish some current that produces magnetic field B, and because of that field you see the flux, and that flux equals to B times A. So that flux increases as you increase current. So here I am writing flux that is going through each loop. If there are n number of turns, then you will get total flux, that is n phi, that will be proportional to current in the coil. So now if I remove this proportionality constant, then I will introduce some constant that is called inductance. Inductance of the inductor. Inductance of the coil, or inductance of the inductor. So if you look at the inductance of the inductor, like your capacitance of the capacitor, it does not depend on, it depends only on its geometrical system. Now maybe like its length and area of the, like for example, if I take a capacitor, the capacitance of this capacitor depends only on its dimensions. A is area of the plate, and D is separation between two plates. Similarly, this is the symbol I will use for inductor, and inductance of the inductor also depends on its length and area of the inductor, like here also, like here. So now the units for inductance is, you can write it's Henry. The units for inductance is Henry. Now here I will have let us discuss what is mutual inductance and what is self-inductance. You take two coils. For example, if I have two coils, let's say one coil is this and next coil is this. First coil and second coil. When you establish current in the first coil, then that produces magnetic field in this coil, and that magnetic field may go through the second coil also. So when magnetic field is going through the second coil, when you alter current in the first coil, that that changes magnetic field in this coil, and the same field is going through this second coil, then you will see change in magnetic field through the second coil. When there is change in magnetic field through second coil, and there will be change in phi, change in magnetic flux, and that change in magnetic flux will induce current in the secondary coil. So here you are getting current in the secondary coil or EMF in the secondary coil because of change in current in the first coil. So because of that, I will call this, see here I said, the total flux through the coil, maybe N is number of turns here, and phi is flux through each coil, and that increases as you increase current in this. So you are getting some constant, and that constant in this case I will call as a mutual inductance. So if you see, in the second case, if for example if I have a single coil and now I am establishing current here, when I establish current here, that produces magnetic field in the same coil. And now when I change this current and this magnetic field also changes, when magnetic field changes, then flux changes. When flux changes, you see the EMF, that change in flux induces EMF in the same coil because you are sending current in the same coil and you are getting EMF, back EMF in the same coil. So we call that, see here, you are sending the current in the coil, and that current is producing magnetic field, and if you change this current, the magnetic field also changes, or as you increase current, magnetic field also increases. So then total flux will be proportional to, once again, I in the same coil, and that proportional constant will be your L, and that is called self-inductance. And because you are looking the EMF in the same coil, you are sending current in the coil and you are looking the EMF in the same coil. So because of that I am calling that constant is self-inductance. And in the second case, you are sending current in some other coil and you are looking EMF in the next coil, and we call it as mutual inductance. Now let us try to derive an equation for mutual inductance. Let us first discuss what is mutual inductance. Now, as I said, in case of mutual inductance, there must be two coils. Let us say two coils, and when you establish current in the first coil, that induces EMF in the second coil. That must induce. When you establish current in the first coil, that produces magnetic field, and if that magnetic field is going through the secondary coil, and you will see flux through the second coil, that is N phi, and that flux increases with current in the primary coil. So you can write N phi is proportional to I, and when you remove that proportionality you get M. That M is called mutual inductance. So consider, for this situation I am considering two coils. Let us consider a first coil is this. Say this is the first coil. So assume that N1 is total number of turns in the coil, and the length of the inductor is a L, and the area of the inductor is A1, or you can call it as A or A1, maybe you can call it as A. So let us say A, and length is L, and say small n is number of turns per unit length, so that will be equals to N1 by L. Okay, and now I am taking one more coil here. Let us take one more coil in such a way that the two axial lines are matching. So that is my second coil. So now second coil, or you can take first anything. Okay, let's take this is the first. Let us call it as second coil, and let us call first one is this one is inside is first coil. Now let us write down the data for second one. Let's say N2 is total number of turns in the second coil, and L is length, because length of both are same, and you can write down A. Let us take A prime is the area of the second coil, and you can write N2 is number of turns per unit length, and N1 is number of turns per unit length of first coil, and N2 is number of turns per unit length of second coil. So now what I am doing, I am establishing current, let us say I2 in second coil first. I am establishing current I2 in the second coil. So now I am establishing current I2. When I establish current I2, that produces magnetic field, let us say B2 equals to B2 equals to mu 0 N2I2. So this is the magnetic field produced by the second coil. And that field, let us draw that field here. That field will go through the first coil also. Now let us see the flux linkage here. The flux that is going through second coil is, because total number of turns in the first coil is N1, then N1 times phi flux is going through that. So that equals to N1, then phi is B2, that is the magnetic field, times area of the second coil. So area of the second coil. Because B2A is the area of the primary coil here. So B2 is the magnetic field inside the coil and A is area of the coil, and there are N1 number of turns, so you can multiply that by N. So that equals to, so let us continue here, N1, and B2 is mu 0 N2 I2 and A. A is area of the first coil. So now N1 phi equals to, you can write down mu 0 N1 small n2 A I2. And even you can write down N1 as, because I have given here, this N1 is number of turns per unit length. So you can write down N1 as N1 by L. L is the length of the coil, the length of the inductor. So you can write down N1 as N1 into L. So let us even do that. Mu 0, then this N1 equals to N1 times L, then L I will place at the end, L, that is I2. So that is your N1 phi. So now this N1 phi is proportional to I2, because as you increase I2, that N1 phi also increases, and see this remaining part is something constant, and that is your mutual inductance. So that mutual inductance, let's say of 1 due to 2, whatever, or 1 with respect to 2, so you can write down M12 equals to mu 0 N1 N2 AL. So this is what your mutual inductance. Even you can modify these equations, because N1 equals to N1 by L, because N1 is number of turns per unit length, and similarly N2 can also be written as N2 by L. So you can also do that, mu 0. So you can write N1 N2 AL, and this by L and this by L, because N1 equals to, because this N1 is N by L and N2 is N2 by L. So now that is mu 0 N1 N2 A by L. So this is also correct equation. So this is the mutual inductance of second coil with respect to first coil with respect to second coil. Now what I will do here, see, you can write down two equations here. Now this is one equation, and this is also correct equation. Now let us see, in the same problem, what I will do now, I will send current I1 through the first coil. Let us see. Now let us draw the same diagram once again. Let us take the primary coil, first coil, like this, and the second coil is this. Axial lines of both coils are matching. So that green one is the second coil, and blue one is, let us say, first coil. Now what I am doing, already I have given data for this. So this is the data, N1 LA, N1 is the specifications of first one, and this is the specification of second one. Now what I am doing, I am sending current I1 through the first coil. If I send current I1 through the first coil, that produces magnetic field inside that magnetic field, let us say B1, that equals to mu 0 N1 I1. So now, because of that magnetic field, see here, there is the magnetic field. That's the magnetic field. So the same magnetic field is going through the second coil also. Now if you look at flux linkage here, then the total flux linkage will be, because there are total N2 number of turns and phi, that equals to N2, that phi is B dot A and B1 dot area of the, because there is no flux, there is no field through the, there is no field at the outer of the first coil, first inductor. So you can, once again you can write down area of the first coil. So now that will be N2 and B1 is mu 0 N1 I1 and A. So that is N2 phi equals to mu 0 N1 N2 A into I1. See, as you increase I1 here, as you increase I1, then this increases. So like here, as you increase I2 here, N1 phi increases. Similarly, as you increase here I1, this increases. So you can write down N2 phi equals to some constant. This is the constant, like here. Like here. So now you can write down some constant. That constant I am writing that mutual inductance of 2 with respect to 1 I1. So now this constant is equals to that one. So now let us write down M21 equals to mu 0 N1, and you can write down N2 as, because small n2 equals to n2 by L, because number of turns per unit length. So you can write down n2 as n2 into L. So you write n2, then I will write down L at the end. So this is what your mutual inductance is. M21 equals to mu 0 N1 N2 A into L. So you are getting the same equation. Here M12 is mu 0 N1 N2 AL, and mu 21 is also mu 0 N1 N2 A into L. So you can write down now for coaxial inductors, M12 mutual inductance of first with respect to 2 is equals to mutual inductance of second due to 1. So that is mu 0 N1 N2 A into L. You can also write down as mu 1, because N1 N2 you can also write down as N1 N2 by L square, and that 1L I am cancelling with this, so you can write as A by L. So let's say that is the inductance of the mutual inductance of the system. So that is mu 0 N1 N2 A by L. So this is what I wrote here. So you can use this equation, you can use this equation or this equation, both are same. So now we can say that mutual inductance of 1 with respect to second is equals to mutual inductance of second with respect to 1. So tomorrow we will continue from here.